Consider the function f of x equals to x square. Observe that as x takes values very close to 0, the value of fx also moves towards 0. We say that limit x tending to 0, f of x is equal to 0. The limit of fx as x tends to 0 is to be thought of as the value which fx should assume at x equals to 0. In general, as x tends to a, fx tends to 1. Then 1 is called limit of the function fx, which is symbolically written as shown. Consider the following function gx equals to mod of x. x naught equals to 0. Observe that g0 is not defined. Computing the value of gx for values of x very near to 0, we see that the value of gx moves towards 0. So, limit x tending to 0, gx equals to 0. This is intuitively clear from the graph of y equals to mod of x for x naught equals to 0. Consider the following function. hx equals to x square minus 4 divided by x minus 2, where x is not equal to 2. Compute the value of hx for values of x very near to 2 but not at 2. You will be convinced that all these values are near to 4. In all these illustrations, the value which the function should assume at a given point x equals to a did not really depends on how is x tending to a. Note that there are essentially two ways x could approach a number a, either from left or from right. That is, all the values of x near a could be less than a or could be greater than a. This naturally leads to two limits, the right-hand limit and the left-hand limit. Right-hand limit of a function fx is that value of fx which is dedicated by the value of fx when x tends to a from the right. Similarly, the left-hand limit. To illustrate this, consider the function fx equals to 1 for x less than equals to 0 and fx equals to 2 for x greater than 0. It is clear that the value of f at 0 dictated by value of fx with x less than equals to 0 equals 1. That is, the left-hand limit of fx at 0 is limit x tending to 0 minus fx equals to 1. Similarly, the value of f at 0 dictated by values of fx with x greater than 0 equals 2. That is, the right-hand limit of fx at 0 is limit x tending to 0 plus fx equals to 2. In this case, the right and left-hand limits are different, and hence we say that the limit of fx as x tends to 0 does not exist even though the function is defined at 0. Let's revise the important concepts which we have studied till now. We say limit x tending to a minus. fx is the expected value of f at x equals to a, given the values of f near to x to the left of a. This value is called the left-hand limit of f at a. We say limit x tending to a plus. fx is the expected value of f at x equals to a, given the values of fx near to the right of a. This value is called the right-hand limit of f at a. If the right and the left-hand limits coincide, we call that common values as the limit of fx at x equals to a and denoted by limit x tending to a, fx. Let's take an example. Consider the function fx equals 3x. Let us try to find the limit of this function at x equals to 2. Solution. For the values in the neighborhood of x equals to 2, the function assumes the value as shown in the table. We observe that as x approaches 2 from either left or right, the value of fx seems to approach 6. We record this as limit x tending to 2 minus. Fx equals limit x tending to 2 plus. Fx equals limit x tending to 2fx equals 6. Here we note that the value of the function at x equals to 2 coincide with the limit at x equals to 2. Let's take another example. Consider the function fx equals x square plus x. We want to find limit x tending to 1fx. Solution. We tabulate the values of fx near x equals to 1 in the table shown. From this, it is reasonable to deduce that limit x tending to 1 minus fx equals limit x tending to 1 plus. Fx equals limit x tending to 1fx equals 2. From the graph of fx equals to x squared plus x, it is clear that x approaches 1. The graph approaches the point 1, 2. Here again we observe that limit x tending to 1. Fx equals to f of 1. Now you will be convinced of the following facts. Limit x tending to 1. X squared equals to 1. Limit x tending to 1. X equals to 1 and limit x tending to 1. X plus equals to 2. Then limit x tending to 1. X squared plus limit x tending to 1. X equals to 1 plus 1, which is equal to, which is again equal to limit x tending to 1, x square plus x. Also, limit x tending to 1, x into limit x tending to 1, x plus 1 equals to 1 into 2, that is equal to 2, which is again equal to limit x tending to 1, x multiplied by x plus 1, that is also equal to limit x tending to 1, x square plus x. Let's take one more example. We want to find limit x tending to 0, fx, where fx equals to x minus 2. For x less than 0, fx equals to 0. For x equal to 0 and fx equals to x plus 2. For x greater than 0. Solution. As usual, we make a table of x near 0 with fx. You can clearly observe from the table that for negative values of x need to evaluate x minus 2, and for positive values we need to evaluate x plus 2. From the first 3 entries of the given table, we deduce that the value of the function is decreasing to minus 2, and hence limit x tending to 0, fx equals to minus 2. From the last 3 entries of the table, we deduce that the value of the function is increasing from 2, and hence limit x tending to 0 plus fx equals to 2. Since the left and the right hand limits at 0 do not coincide, we say that the limit of the function at 0 does not exist. Here, we remark that the value of the function at x equals to 0 is well defined and is indeed equal to 0. But the limit of the function at x equal to 0 is not even defined. Let's consider another example. We have to find limit x tending to 1 fx, where fx equals to x plus for x not equal to 1 and fx equals to 0 for x equals to 1. Solution. As usual, we tabulate the values of fx for x near 1. From the values of fx for x less than 1, it seems that the function should take value 3 at x equals to 1. That is, limit x tending to 1 minus fx equals to 3. Similarly, the value of fx should be 3 as dictated by values of fx at x greater than 1. That is, limit x tending to 1 plus fx equals to 3. But then the left and the right hand limits coincide and hence limit x tending to 1 minus fx equals limit x tending to 1 plus fx, which equals limit x tending to 1 minus fx, that is equal to 3. Here we note that in general, at a given point the value of the function and its limit may be different even when both are defined.